Welcome. In this video, I will present my deep learning project. My work supports Dan Lynch's PhD project. He studies optimal control algorithms for legged robotic locomotion. His project started during Northwestern's Robot Design Studio course, where Dan's team built a hopping robot, shown on the right. Dan decided to focus his future efforts on creating optimal controllers for legged robots on soft terrain. Dan's approach requires models of how the robot feet interact with soft ground. There are two parts to the project. In the first part, I use supervised techniques to learn a model of how the yielding terrain affects the robot's foot. In the second part, I used reinforcement learning algorithms to have the robot learn to walk on soft ground. Let's dive into the first part. So, we want to learn a model of how the ground affects the foot as the foot intrudes into the granular material. Georgia Tech's Pterodynamics lab has done experimental work on how granular material affects robotic feet. We recreated one of their experimental setups in a DEM simulation. Below on the right, you can see a GIF of what our experimental setup looks like. A plate is repeatedly dropped into a bed of granular material. On each drop, it has a different angle of attack and angle of orientation in the plane. Moreover, we also drop it at varying speeds. From this, we gather a larger data set. Below you can see three pairs of heat maps. These represent the magnitudes of the stresses per unit depth as a function of the foot's orientation in the plane and the foot's direction of motion into the granular material. The Pterodynamics raw data is from a physical experiment. The DEM data is from our recreated simulation of the Pterodynamics experiment. On the right is the neural network's learned mapping from the foot orientation and foot direction of velocity to stress per unit depth. From this dataset, we can reasonably infer that the DEM simulation is capturing the essential physics of the Pterodynamics experiment, and moreover, that the neural network is also capturing that. With confidence that the DEM simulation is capturing the physics well, and that a neural net was also representing the function well too, we increase the input space of the neural network. The new neural network's input space includes the position, orientation, and velocity of the foot, as well as the depth of the foot into the granular material. Below is a comparison of the neural network, RFT, and DEM data. To generate these plots, we ran the DEM simulation forward once to gather a trajectory of the foot through the granular material. At each time step, we use the given state of the foot as input to the RFT model and neural network model to predict the ground forces and torques. Below are the results. The ground truth is in yellow, RFT is in blue, and the neural network is in orange. For part 2 of the project, I set out to have the robot learn to hop using reinforcement learning. I read a lot about reinforcement learning and began to gain intuition by implementing simple RL algorithms such as Q-learning, deep Q-learning, and double deep Q-learning. I then moved on to more recent continuous control environments that are better suited for our task at hand. To validate my algorithms, I tested them in OpenAI gyms. The algorithms most suited to this problem are DDPG and TD3. I implemented both in OpenAI gyms for simple monoped robots whose task is to learn how to walk by controlling its joints. Below are some of the results. The robot learned a very nice control policy under DDPG. I then created custom OpenAI gyms to approximate Dan's hopping robot. I used the neural network from part 1 to model the soft ground in PyBullet. Below is an image of the environment. The soft ground is shown in blue, and the robot is in gray. At a high level, its goal is to learn how to walk in the forward X direction. I then implemented a policies modulated trajectories generators architecture for our hopping robot. This method allows the designer to incorporate prior knowledge about desired trajectories into the learned policy. The agent learns to control a new dynamical system, that of the robot and its controller, rather than the robot directly. This method requires a trajectory generator. We use Dan's optimal wrench generator. At each time step, the robot can modulate the trajectory generator itself, and also add modulation terms to the output of the generator. The agent must learn how to control the system, that is the robot and its controller. Below is an image describing the flow of information in a PMTG architecture. gain intuition, I implemented the toy problem in the original PMTG paper. The control problem is to have a ball follow a specified path in the plane. Say we know the desired path is roughly a figure 8. We can define a trajectory generator parameterized by 2 values then. Below on the right is an image of 3 trajectory generators with unique values, and on the left is the optimal trajectory, which is roughly a figure 8. The agent must then learn how to set the parameters of the trajectory generator and also add correction terms to the output of the trajectory generator so that the ball follows the optimal path. Below are my results on the PMTG toy problem. On the left, you see in blue the optimal path, which is roughly a figure 8. In orange is the learned path of the ball through space over time. On the right is the cumulative reward per episode that my PMTG architecture achieves over time. To create a PMTG architecture, we needed a trajectory generator. We modified Dan's open-loop controller for monoped locomotion on soft ground to fit our needs. Dan's controller is parameterized by endpoints. These points define 3 separate curves over time. Each curve defines a component of the planar wrench that the foot should exert as it locomotes on soft ground. Below on the right is an image of the planar wrench curves over time. The first half of the curves is the stance phase, and the second half is the flight phase.